Alright, as we continue in section 2, we are going to write some more electron configurations, but I don't know about you, but I got kind of tired of all of those little arrows, so I'm going to show you some couple shorthand notations in how to show electron configurations. The electron configuration notation eliminates the lines and the arrows that we had in orbital notation. So it shows the total number of electrons in the sublevel as a superscript after the letter. So this was oxygen we saw earlier with 8 electrons. So this shows 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and 4 electrons in the 2p sublevel. So all that together shows the electron configuration notation. Alright, we're going to practice. We're going to use the same 2 elements that we used for in the notes previously. Aluminum has 13 electrons. So we know that the first main energy level is 1, and the first main energy level has a 1s sublevel. S sublevels have 1 orbital. 1 orbital can hold 2 electrons. After the first main energy level comes, of course, the second. The second main energy level with 2 sublevels has a 2s and also a 2p, but first we'll deal with the 2s. 2s sublevels have, s sublevel has 1 orbital. 1 orbital can hold 2 electrons. After the 2s comes the 2p sublevel. P sublevels have 3 p orbitals. 3 orbitals, 2 electrons, that makes 6 electrons total. That's 10 electrons. If I add all 6 and 2 and 2 makes 10. I need 13. So after 2p, I look at the off-bow principle and I get 3s. S sublevels hold 2 electrons. And after 3s comes 3p, and I only need 1 more electron. So while the 3p could hold 6 electrons, in aluminum we only have 1 electron in the p sublevel. So that was much quicker and within all of those arrows. For zinc, zinc has 30 electrons, a 30 atomic number. So we will continue with the 1s sublevel and start there. 2 electrons in the 1s. After the 1s sublevel comes the 2s. S sublevel, 1 orbital, 2 electrons. After the 2s comes the 2p. The 2p can hold 3 orbitals with 6 electrons total. After the 2p comes the 3s. 3s can hold 2. And after the 3s comes the 3p. Again, the 3p orbitals, 6 electrons. After the 3p, according to we might think that 3d comes next, but the off-bow principle says that 4s gets electrons first. So the 4s sublevels can hold 2 electrons. After the 4s now comes your 3d. And your 3d electrons, d has a total of 5 orbitals. That makes 10 electrons. So counting that up, that should make 30 electrons total, and it does. Now, while this is much shorter than the orbital notation by eliminating the lines and arrows, we can actually get it even shorter. What you might notice is at the beginning of both of these electron configurations are exactly the same. And what we will find is that through many of these, the lower level electrons are all exactly the same. So those are the electrons, while they are important, they are electrons that we're really not concerned about, and it's these last electrons out here at the end are the ones that we are looking at, because these are the ones that determine an element's chemical properties. So in this last shorthand notation, we call this noble gas notation. So noble gases, they are called that because they are non-reactive and they are non-reactive because they have all of their energy sublevels totally full. So it is a shorter way to write the electron configuration. You substitute the configuration of the noble gas before the element you're looking for. You put the symbol in the brackets, and then you pick up from there. And how you know where to start is you start with whatever S sublevel that the period of your element is in. And periods go horizontally across the periodic table. So writing all out the electron configuration of scandium, I see all of these different elements, different electrons. If I count backwards on the periodic table from scandium, and I find the next noble gas that's previous, I find argon. This is the electron configuration for argon. Notice that up until the 3p6, it is exactly the same. So instead of writing out all of the configuration for scandium, I'll take the symbol for argon, put it in square brackets, and that represents all of the configuration of the element argon. Now scandium, which is a total of 18 electrons. So where do I start in putting the electron number 19? Well, if I look in scandium, is found in period number 4. So I start with the 4s, so 4s2, and then 3d1. And that's all that's left to make 18, 20, 21 electrons. So let's practice again. Again, aluminum having 13 electrons. If I look at aluminum, atomic number 13, and count backwards from aluminum, when I count backwards from aluminum, the noble gas I come to is neon. Now neon has 10 electrons. So this neon right here represents a total of 10 electrons in the configuration for argon. I'm sorry, aluminum. Aluminum is found in period 3. So after I have this 10 electrons, I will know that I should start with period 3. So 3s is where I would start. So 3s and s sublevel can hold 2 electrons in addition to the 10 I already have in the brackets. So that gives me 12. So after the 3s, I have the 3p, and it just needs 1 electron. We can do the same thing for zinc, and it's 30 electrons. So when I count backwards from zinc, I get argon as my noble gas. Argon having 18 electrons. So argon is where I start. Now, zinc is found in period 4, so I'll start with the 4s sublevel. S sublevels can hold 2 electrons. After the 4s, according to the off-bow principle, comes the 3d. The 3d sublevel, d has 5 orbitals, so that makes 10 electrons total. After, that's 18. You make sure you keep track of your electrons. 18. Looks like that makes 30. So then this would be the total configuration in noble gas notation for the element zinc. Much shorter than all those lines and arrows. So to summarize, the 3 types of notation you'll need to be able to do to show where all the electrons are orbital notation, electron configuration notation, and noble gas notation.